Interstellar Objects and Earth. Assessing the hidden impact risk interstellar objects, ISOs, rocks and ice from other star systems are a newly appreciated hazard to Earth. While only 3 have been confirmed passing through our solar system, Oumuamua, 2L/Borisov, and the current visitor 3I Atlas, their potential for catastrophic impact is significant, yet poorly understood. This is not merely an academic question. The solar system's early history was defined by violent collisions, and while large impacts are rarer now, the continuous influx of ISOs maintains a persistent, if unpredictable, threat. The unseen stream of interstellar visitors for 4.6 billion years, ISOs have been entering our solar system. Though most miss Earth entirely, the sheer number over geological time suggests some have struck our planet, potentially creating ancient impact craters like the massive Vredefort structure in South Africa. Unlike asteroids and comets originating within our system, ISOs approach at much higher speeds, making them harder to detect and more destructive if they do hit. New research, mapping the threat. A recent study, the distribution of Earth-impacting interstellar objects, led by Daryl Seligman at Michigan State University, attempts to quantify this risk. The research doesn't focus on how many ISOs exist, that's currently unmeasurable, but rather on where they're likely to come from and when they might strike. The scientists simulated a population of 1 billion ISOs ejected from M-dwarf stars, red dwarfs, the most common type in our galaxy. Key findings: direction, timing, and vulnerable zones. The simulations reveal that ISOs are twice as likely to originate from 2 areas: the solar apex, the direction the Sun travels through the Milky Way, and the galactic plane, the disc-shaped region containing most stars. This is due to the Sun's motion and the higher density of stars in the galactic plane. Counterintuitively, the ISOs most likely to hit Earth move slower than average, as gravity can preferentially capture slower objects into Earth-crossing orbits. Seasonal risk. The highest impact velocities occur in spring, when Earth moves toward the solar apex. However, winter sees more potential impactors due to Earth's position toward the solar antapex, where the Sun moves away from. Geographic vulnerability. Low latitudes near the equator are at greatest risk, with a slight bias toward the northern hemisphere, home to most of the human population. Limitations and future prospects. The study explicitly acknowledges its limitations. The simulations are based on ISOs ejected from M-dwarf systems, and the actual distribution may differ if other stellar types dominate. However, the researchers believe the core findings, directional biases, and seasonal variations, likely hold true regardless of the source stars. These distributions are only applicable for interstellar objects that have M-stars kinematics. Different assumed kinematics should change the distributions presented in this paper. The work primarily informs future observations. The upcoming Vera Rubin Observatory, with its Legacy Survey of Space and Time, LSSD, will provide real-world data to validate or refute these simulations. Conclusion: ISOs represent a long-term, though low-probability, existential risk to Earth. While current estimates remain speculative, this research provides a crucial framework for future detection efforts and hazard assessment. The era of recognizing interstellar threats is only just beginning.